Imagine you're watching a completely average tennis player step onto the court. And, you can tell immediately that they are just struggling.
Right, like totally out of their depth.
Yeah, exactly. I mean, they're sweating, missing half their serves, hitting the ball directly into the net. They just look totally overwhelmed by the speed of the game.
Sure.
But then a coach walks out, and the coach stops the game entirely and just, watches this player swing the racket exactly 3 times.
Just 3?
Just 3 times. But instead of giving the player verbal advice on their form, like bend your knees or whatever, the coach walks onto the court, dynamically rebuilds the racket to have a massive head, lowers the net by 2 feet, and literally reshapes the physical boundaries of the court itself.
Wow. Okay.
Right? And then the game resumes, and suddenly that exact same average player is hitting aces, like 99.3% of the time.
Which sounds completely absurd.
It sounds like magic, or
Yes.
honestly, like cheating. But what if I told you that this exact scenario is happening right now? Not in sports, obviously, but in the bleeding edge of artificial intelligence.
It is, it's really the perfect metaphor for what we're looking at today. So welcome to our deep dive into the foundations and frontiers of generative AI.
Yeah, so glad to be jumping into this one.
Our mission for this deep dive is to explore a pretty radical new framework. It takes tiny, incredibly cheap small language models, or SLMs, and makes them perform like those massive, incredibly expensive frontier models.
Which is the dream, right?
Exactly. And the real kicker is it does this without breaking your budget and, crucially, without violating enterprise data privacy.
Right, which is huge. So the source for our deep dive today is this groundbreaking paper, and it's titled Compiling Deterministic Structure into SLM Harnesses.
Quite a mouthful.
It really is. But the jaw-dropping finding we are going to unpack is exactly what I just described in that tennis metaphor. I mean, this paper outlines a system that takes a lightweight AI from a failing like 48.3% accuracy rate on highly complex tasks, all the way up to a 99.3% accuracy rate.
It's just a staggering leap.
And it achieves that leap using only 3 training examples. Not 3,000, not 3 million. Literally, just 3.
Which, completely defies the conventional wisdom of how machine learning is supposed to work.
Right. Because usually it's all about the data, isn't it?
Oh, absolutely. Typically, we think of AI improvement as a brute force numbers game. Like if you want better accuracy, you just assume you need to feed the model mountains of data.
Right, and burn through immense computational power to update the internal neural weights.
Exactly. But this paper takes an entirely different, almost philosophical path. It asks a fundamental question. What if the problem isn't the model's brain, but the environment we're forcing that brain to work in?
Okay, let's unpack this. Because to really understand why this is such a game changer, we have to look at the daily reality for most businesses right now. I mean, we are all dealing with massive information overload.
Oh, totally.
Every enterprise wants to use AI to, process invoices, parse insurance claims, analyze thousands of bank statements, but they face a very real dilemma when it comes to actually deploying this tech.
Right. It's the classic enterprise AI dilemma. Let's say you're a bank. You simply cannot legally or even ethically send all of your highly sensitive customer financial data to some generic public cloud API.
Right, you can't just throw that into a massive frontier model like GPT-5 or Gemini.
Exactly. There are incredibly strict data sovereignty restrictions and regulatory compliance laws. And on top of that, running those massive models for millions of high-volume daily tasks is just prohibitively expensive.
Oh, I bet.
You're basically paying for a supercomputer to do basic arithmetic.
Yeah, it's like relying on frontier models for daily corporate paperwork is like hiring a famous, wildly expensive polymath just to sort your company's mail.
That's a great way to put it.
I mean, yes, it works, but you will go bankrupt doing it. So enterprises pivot. They look at small language models, SLMs. These are lightweight, they're cheap, and you can run them securely on your company's own local servers.
Right, so you keep your data, you save money. Problem solved, right?
Would think so, but no.
Not quite.
Hmm?
And this is where the paper introduces a really critical concept called epistemic asymmetry.
Epistemic asymmetry, okay.
Yeah. So small language models have heavily reduced parameter counts. They're great at basic text generation, maybe summarizing a simple paragraph, things like that.
Sure.
But they lack the neural real estate, the internal capacity to self-correct their own reasoning errors. When an SLM makes a logical mistake, or, hallucinates a completely fake number in a financial document, it doesn't know it made a mistake.
Oh, wow. It just confidently believes it's right.
Exactly.
So it's literally exactly like hiring an eager intern who confidently does the math wrong and has absolutely no idea they've messed up. They'll just hand you a completely botched financial report with a big smile on their face, fully expecting a gold star.
That is exactly what it's like. Because of this epistemic asymmetry, you just can't trust the SLM to judge its own work. If the student agent must perform the task and also act as its own quality assurance team, it fails.
Right.
The authors of this paper realize that because these tiny models can't fix their own internal logic through continuous weight updates, they just don't have the brain power, we have to stop trying to train the intern.
Okay, so if we're not training the intern, what are we doing?
We have to build a better, more rigid environment around them so that they physically cannot make that mistake.
Oh, I see. Which means we are changing the office, not the intern. So how exactly do we do that?
Through a discipline called harness engineering.
Harness engineering?
Yeah, the harness is the non-model infrastructure surrounding the AI. We're talking about the system prompts, the tool chains, the routing logic, the Python scripts. It's all the scaffolding that makes the agentic behavior reliable.
Okay, that makes sense.
And the paper proposes a framework to automatically optimize this exact harness, which they call SGDe.
Right, SGDe, which stands for Semantic Gradient Descent. And I noticed they specifically point out the trailing lowercase e in the paper.
Yes, they do.
That's to distinguish it from the traditional stochastic gradient descent that machine learning usually relies on, right? Let's break down that difference because it feels like the core of the whole paper.
It really is the absolute core. So think of traditional AI training stochastic gradient descent, like a volume knob on a stereo.
Okay.
You're operating in a continuous mathematical space. You're smoothly turning the math up and down, making tiny numerical tweaks to the continuous weights inside the neural network to get the sound just right.
Right, tweaking the brain itself.
Exactly. But SGD operates in a discrete semantic space.
Meaning what, exactly? Like instead of a volume knob, it's like a control panel of light switches.
That's a brilliant way to put it, yeah. Instead of smoothly adjusting numbers, you are flipping discrete switches. SGD doesn't touch the small model's internal weights at all.
Wait, not at all.
Not at all. Instead, it systematically rewrites the actual text of the system prompts, generates brand new Python code, and physically changes the graph structures of the workflow itself. It alters the hard environment.
Okay, but this sounds incredibly complex. I mean, how does the system automatically know how to write new code or change the prompts? A small model definitely can't do that.
It doesn't. And this is where they introduce a strict teacher-student architecture. They entirely decouple the execution of the task from the optimization of the task.
Oh, okay, decoupling them.
Right. So for the daily high-volume work, you have the student model. In the paper's experiments, this is Quen 2.5 1.5b.
Which is a tiny model.
Exactly. It's a highly quantized model.
And just to clarify for everyone listening, when we say quantized, we mean the model has been mathematically squished down, right?
Right.
Like it uses lower precision numbers so that it can run lightning fast on totally normal, cheap hardware instead of, massive server farms.
Correct. And the student is completely blind to the optimization process. It acts strictly as a compiled execution engine. It just blindly follows the flowchart it is handed.
Okay, so the student is just executing. Who is writing the flowchart?
The optimizer is the teacher model, and the teacher is a massive frontier model, in this case, Kimi 2.5. The teacher acts as the offline manager.
Okay.
It literally reads the text execution logs of the student, spots exactly where the student hallucinated or failed, generates a natural language critique of that failure, and then writes a completely new piece of Python code or a new prompt to permanently patch that hole in the flowchart.
Wait, I have to push back here.
Sure, go ahead.
If we still need to pay for a massive, expensive teacher model like Kimi 2.5 to do all this complex error analysis and code writing, aren't we defeating the whole purpose? I mean, doesn't that completely ruin the cost savings and the data privacy we were supposed to get from using the small model in the first place?
It is a totally valid concern, and honestly, it's the exact trap that many traditional distillation techniques fall into. But the brilliance of SGD is that the teacher only operates offline.
Offline.
Yes, strictly during the setup phase, on a minuscule batch of anonymous sample data.
So it's not looking at our real live customer data.
Never. The teacher looks at maybe 5 or 10 dummy examples. Once the teacher compiles the optimized flowchart, the teacher's completely disconnected, goes away entirely.
Oh, wow.
Yeah. The student is then deployed in production, completely on premises, securely handling millions of real-world enterprise documents all on its own. using the bulletproof flowchart the teacher left behind.
Got it. Okay, so the famous polymath comes in for one single afternoon, looks at a few dummy letters, sets up the mailroom sorting system, writes the instruction manuals, and then just leaves the building.
Exactly.
And from then on, the eager intern just follows the manual forever.
That is the exact dynamic. So how does the teacher actually physically alter the student's environment?
Right. How does it do the harness engineering?
Well, the paper breaks this harness optimization down into two distinct levels. The first is dynamic granularity.
Dynamic granularity.
Yeah, which is essentially adjusting the cognitive load on the small model.
This is where the coach starts reshaping the tennis court, right? What does that actually look like for an AI?
Let's use a real-world enterprise example.
Mm-hmm.
Imagine the student model is tasked with reading a complex 20-page commercial insurance claim, extracting 5 specific liability numbers, and then calculating the total payout based on a deductible formula.
Sounds like a lot for a tiny model.
It is. If the student fails, the teacher reads the log and asks, why did it fail? And very often with small models, the failure is due to context bloat or attention degradation.
Meaning, the model's internal spotlight got stretched too thin.
Yes.
Like it tried to hold the 20 pages of text, the 5 numbers, and the math formula in his head all at once, and it just dropped the ball.
Exactly. So the teacher steps in and performs what the paper calls node decomposition.
Node decomposition, chopping it up.
Exactly. It takes that one massive, overwhelming step in the workflow and literally chops it up into a chain of smaller, highly sequential subnodes. It rewrites the instructions to say, first, just read page 3 and find the incident date. Stop.
Yeah.
Next, find the deductible amount. Stop. It creates a hyper-granular step-by-step pipeline, so the small model spotlight is perfectly focused on one tiny thing at a time.
But I imagine making 1,000 tiny steps is incredibly slow, right? Doesn't that waste computing power? Does it ever go the other way?
It does, actually. If the teacher is analyzing the logs and notices that there are 2 consecutive steps in the workflow that are redundant.
Like what?
Well, maybe extracting the client's zip code in one step and then verifying your state in the next. It realizes that doing them separately just burns computing time without actually improving the accuracy.
Oh, I see.
So it performs node fusion. It merges those 2 steps back into a single prompt.
That is so relatable. If you think about your own daily workflow, it's the exact same psychological process.
Oh, for sure.
You realize you're totally paralyzed by a massive, ambiguous project, so you naturally break it down into a highly granular checklist just to get started. Node decomposition.
Exactly.
Or you look at your calendar and realize you have 2 useless back-to-back status meetings that could just be combined into a single 5-minute email. Node fusion.
Yep. The teacher is custom-fitting the architecture of the task to the exact cognitive limitations of the student's brain. But, adjusting the granularity is only the first half of the magic.
There's more.
Oh, yeah. Once the overarching task is broken down into perfectly sized pieces, the teacher has to decide how each individual piece should be executed. And this brings us to the compilation toolkit.
Right, and looking at the paper, the teacher has 3 specific choices for every single node in the workflow. It's not just rewriting prompts.
Right. The first choice is the most basic, prompt refinement.
Okay.
The teacher decides to keep the step as a standard LLM text generation call, but it rewrites the natural language instructions to be clearer and more specific. This is what existing prompt optimizers already do.
Right. Fairly standard.
But SGDe goes much further with its second choice.
Oh, choice number 2 is capability offloading. And this is the part that really blew my mind when I read it.
It's fascinating.
Let's say the step requires the SLM to do that complex deductible math we talked about. We already know the small model is terrible at math because LLMs are fundamentally just predicting the next word probabilistically. They aren't calculators.
Right.
So what does the teacher do? It completely removes the SLM from the equation for that specific step.
It literally deletes the LLM mode and replaces it. The teacher writes a deterministic Python script instead.
Wow.
The SLM is now restricted purely to reading the text and extracting the raw numbers. Once it hands over the numbers, the LLM goes to sleep and the Python script takes over to calculate the exact mathematically perfect answer.
I love that. It takes the calculator away from the eager intern and permanently glues it to their desk so they are physically forced to use it.
Yes.
The intern isn't allowed to do math in their head anymore.
Exactly. It completely sidesteps the epistemic asymmetry we talked about earlier. The probabilistic AI is no longer allowed to guess at math.
That makes total sense.
But what happens when a task can't be solved with a rigid Python script? What if it requires nuanced reasoning, but the small model is just highly variable? meaning, sometimes it gets the reasoning right and sometimes it hallucinates.
Okay, yeah, this leads to the third choice, right? Structural consensus.
Right.
If the teacher sees the model is inconsistent, it creates what the paper calls a fan-out, fan-in subgraph.
Sounds technical, but it's pretty intuitive.
It is. It basically takes that single prompt, replicates it 3 times with slight temperature variations, and runs them in parallel. So it essentially asks 3 clones of the intern the exact same question.
Exactly.
Then it uses a Python script to run a strict majority vote on the 3 answers to pick the final result.
Right. It is forcing the model into self-consistency by applying the law of large numbers to reasoning, by combining capability offloading for the hard math and structural consensus for the fuzzy reasoning. The whole system fundamentally shifts.
Yeah, it transitions from being a probabilistic text guesser into a deterministic, reliable software machine.
Precisely.
Okay, so the theory is incredibly elegant, but I really want to talk about the actual jaw-dropping results this produced, because this is where the paper challenges everything we thought we knew about AI training.
Let's get into the numbers.
The researchers ran adversarial testing on a dataset derived from GSM-hard.
Which, for context, is a notoriously brutal mathematical reasoning test.
Oh, really?
Oh, yeah. And the researchers didn't just use the standard test. They purposefully synthesized a set of questions that they knew the student agent failed at consistently.
Sneaky.
They really wanted to push this tiny model to its absolute breaking point to see if the harness could save it.
And the baseline accuracy for the tiny student model out of the box was a dismal 48.3%, basically failing. They then applied to DSPy, which is currently a state-of-the-art prompt optimizer. DSPy boosted the accuracy to 65.0%, but then it completely hit a ceiling.
Yeah, because it could only change the text of the prompts. It couldn't alter the actual structure of the code or offload the math to Python.
Exactly. But then they applied the SGDe framework, and with just 5 training samples, meaning the teacher only analyzed 5 examples of the student failing, the student's accuracy skyrocketed to 91.3%.
That alone is incredible. But the bombshell is what happened when they actually reduced the amount of training data.
Yes. When they gave the teacher only 3 training samples to look at, the system hit 99.3% accuracy. I have to stop here. Mathematically, how is less data better?
It sounds impossible.
We are trained to think big data is king. Millions of rows of data equals intelligence. How on earth does looking at 3 examples produce a near-perfect AI?
This is truly the most profound insight in the paper. They formalize this phenomena as resource-bounded PAC learning.
PAC-learning.
Yes. PAC stands for probably approximately correct. It's a statistical framework that calculates the sample complexity, basically how much data you need to learn a specific task.
Okay.
Think of searching for a solution like searching for a lost set of keys.
Okay, I'm with you. Searching for keys.
In traditional continuous neural network training, the hypothesis space, the number of possible parameter combinations, is essentially infinite. It's like searching for your lost keys across the entire planet.
Which is why you need millions of data points to guide you.
Exactly. But in SGDe, the hypothesis space is heavily artificially restricted.
Right, because the teacher isn't searching infinite math equations, it's just choosing between a few discrete options.
Yeah.
Change the text, write a Python script, or set up a majority vote.
Exactly. You're no longer searching the planet. You are only searching 3 rooms in your house.
Wow, that's a massive difference.
It is. Furthermore, the teacher model acts as an incredibly strong statistical prior. Yes, a prior is essentially a massive head start. The giant teacher already knows how to write Python code. It already understands complex logic. It doesn't need to learn how to solve the math problem from scratch.
Right.
It only needs to observe the specific ways the student model is dropping the ball so it can map what it calls the offloading feasibility.
Oh, I see. It just needs to watch the intern trip a few times to know where to put the handrails.
Precisely. The teacher only needs to see the failure about 3 times to perfectly recognize the pattern. The student always fails at the arithmetic step on page 2. I will replace page 2 with Python.
So why did 5 samples actually perform worse than 3? I mean, why did it drop from 99 to 91%?
Because in discrete heuristic optimization, the composition of your batch matters much more than the size of your batch. Adding those 2 extra samples introduced what they call trace variances.
Meaning random noise.
Basically, yeah.
It's like you were perfectly searching the 3 rooms for your keys, but the extra data distracted you, and you started looking in the couch cushions because you found a shiny wrapper.
That's a great analogy. The extra variance temporarily confused the optimizer into building a slightly less efficient flowchart, causing a slight dip in accuracy before it eventually stabilized again if you added even more data.
Huh.
This is known as the small m paradox. It proves mathematically that you do not need big data if you have a brilliant teacher dynamically reshaping a highly restricted environment.
It goes right back to the coach watching 3 tennis swings and saying, I've seen enough, I know exactly how to rebuild this court.
Exactly.
But as we know, every scientific paper has boundary conditions. Nothing is magic. If I try to deploy this in my company tomorrow, what breaks the system?
Well, this raises the critical issue of task homogeneity. The PAC-learning math guarantees this incredible 3-sample efficiency only if the tasks in that batch are structurally similar.
Well, okay, so what happens if they aren't?
To test the boundaries, the researchers created a mixed task test set. They took highly divergent tasks, for example, combining complex financial math problems with creative story writing assignments, and put them into the exact same training batch.
Oh boy, let me guess. The system tried to build a harness that could do both, and it completely failed.
Yes. Performance plummeted right back down to 48.7%, barely better than the baseline. They call this topological overfitting.
Topological overfitting, why does that happen?
Because it violates what is called the realizability assumption.
Realizability assumption.
Yes. This is the assumption that a single perfect flowchart even exists for the tasks you are giving it. When you mix math and poetry, that assumption is false.
Ah, I see.
The teacher tries to build one universal flowchart, a Frankenstein workflow, and the rigid Python structures it builds to solve the math problems end up subtly destroying the model's ability to be creative for the writing tasks.
Right. So if one master workflow breaks because the tasks are too different, it sounds like we need to stop looking for a one-size-fits-all solution. Can we just build multiple separate courts for different sports?
That is exactly the fix the paper proposes for future work. They call it mixture of topologies, or agentic routing.
Agentic routing. Okay.
Instead of trying to build one giant monolithic graph for your entire enterprise, you build aggressively compartmentalized, highly narrow subgraphs, one for invoices, one for emails, one for claims.
Makes sense.
Then you place a lightweight intent classifier at the very front of the system.
Oh, like a traffic cop standing at the door.
Exactly.
You type a prompt, the traffic cop looks at it and says, oh, this is a compound interest query. Route this to the hyper-specialized financial math subgraph. Or, this is a document translation request. Route it to the linguistics subgraph.
Yes. By compartmentalizing the routing, the teacher can optimize each individual subgraph to near-perfect accuracy using just 3 examples, without any of the wildly different tasks interfering with one another.
Wow. Let's summarize what we've unpacked today, because the implications here for anyone trying to actually use AI in the real world are just massive.
They really are.
The main takeaway is that we have been treating AI like a brain in a jar that just needs to get bigger and bigger. But we don't always need a massive monolithic brain to solve enterprise problems. We don't need to spend millions of dollars on compute, and we don't need to compromise our sensitive data.
No, we don't. By utilizing a teacher model offline to build a discrete, rigidly optimized harness of Python code and consensus voting around a tiny model, that cheap SLM can achieve near-perfect accuracy.
It's incredible.
We are shifting our entire philosophy from optimizing the internal weights of the model to optimizing the external architecture of the system.
And for you listening, as AI continues to integrate into your workplace and your daily workflow, the most successful, reliable systems you interact with aren't necessarily going to be the ones boasting the most neural parameters.
Not at all.
They are going to be the ones with the smartest structural orchestration, the ones that know exactly when to let the probabilistic AI think and when to force it to use a deterministic calculator.
It redefines what an AI agent actually is today. It is no longer just a neural network operating in isolation. It is the synthesis of the model and its carefully engineered environment.
Which leaves us with a final, slightly philosophical thought to mull over.
I love these.
If an AI system can be designed to dynamically rewrite its own software architecture to cover up its own cognitive weaknesses, where do we actually draw the line between the model and the program? Next time you ask an AI a highly complex question and get a brilliantly perfect answer back, ask yourself, are you talking to a genius brain, or are you just talking to a beautifully engineered harness?